functions in calculus that we'll cover. You'll use Taylor and Maclaurin series in all kinds of applications, and you'll see it again more recently in your differential equations course. We're talking about functions that have n continuous derivatives over some interval. We're looking to find a polynomial that fits the points of f in that interval that contains a point x is equal to c. In other words, the power series behaves like the function does for all values of x in that interval. Now the nice thing about this is a power series is a polynomial, where the function might be some transcendental, complicated thing. So if we can do things to this polynomial, like function evaluations, term by term differentiation, term by term integration, then those alterations behave as the function near that point. So let's start building it. We're talking about taking our function and representing as a polynomial of the form a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, and so on. So let's find out what these subscripted a's are, these coefficients. So if you plug in c for x, notice that all the terms will disappear except for a0. So this polynomial has the same y-intercept as f of x. Now let's take a derivative. Take the derivative of that polynomial. The derivative of a0 is 0. The derivative of x minus c is 1, so we get a1. Then we'll take the derivative of x minus c squared and get 2a2 times x minus c to the first. Then we'll take a derivative of the next one and get 3a3 times x minus c squared. And then we've got all those higher power terms. Substitute c in for x, and we get a1, because all the remaining terms would have zeros in them. So this is a function whose slope at x is equal to c is the same as the coefficient of the x minus c term. Let's take another derivative. The second derivative is going to give us, the derivative of a1 will be 0. The derivative of x minus c is going to be 1, so we get 2 times a2. The derivative of x minus c squared will give me 2 times 3, a3 times x minus c to the first, and then the other terms. The second derivative, when x is replaced by c, leaves us only with 2a2, because all these other terms will have an x minus c in it. So that says that f double prime at c divided by 2 is going to be a2. So let's now look at the third derivative. Okay, so we're going to go back here and take another derivative. The third derivative of f, that's x first. Third derivative of f at x, well, the 2a2 will have a derivative of 0, and then we'll have 2 times 3 times a3, and then the derivative of x minus c to the first is going to be 1. So that f, and everything else, there's going to be a term out here that's going to have a, let's see, maybe I should put another term out here, plus a4 x minus c to the fourth. Okay, so another derivative here would be, first derivative would be 4a4 times x minus c cubed. Your second derivative will have a 3 times 4 times a4 times x minus c squared. And so here, if I take a derivative of that, it'll give me a 2 times 3 times 4 times a4 times x minus c, and there's an infinite number of terms behind here. But at x is equal to c, all these terms out here will be 0, and we'll get 2 times 3 times a3, so that a3 is equal to the third derivative at c divided by 2 times 3. And so I'm going to write that as the third derivative at c divided by 3 factorial, since 3 factorial is 3 times 2 times 1. The fourth derivative you'll see is, you'll see that the fourth derivative at c is going to give us 2 times 3 times 4 times a4. So that says that a4 can be written as the fourth derivative of c divided by 2 times 3 times 4, which says that a4 is the fourth derivative at c divided by 4 factorial. So now we know what all of the coefficients look like. All of the coefficients can be written as that order derivative of f evaluated at c divided by the factorial that matches whatever derivative order we're on. And so that gives us this definition of a Taylor polynomial. A Taylor polynomial is a polynomial that represents this infinitely differentiable function y is equal to f of x in an interval containing x is equal to c. It has the form of f of x is f of c plus f prime of c over 1 factorial times x minus c to the first plus f double prime at c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed, and on and on and on, so that the nth term would look like the nth derivative of f at c over n factorial times x minus c to the n plus some remainder function, where that remainder function is a polynomial that looks like the n plus first derivative of f evaluated at some zn depends on x, divided by n plus 1 factorial times x minus c to the n plus 1. Zn is some number between c and x. And based upon your needs for this polynomial, you can control the size of that remainder, or you keep building the polynomial until that remainder has the size specified for the needs of your application. But in general, we're talking about a Taylor series, so we write it as an infinite series. All right, we don't have to stop. We can do an infinite series where all the coefficients are the order of the derivative evaluated at c divided by the factorial that corresponds to the order of the derivative times x minus c to the n power. So the power on the x minus c continues to climb. So when you're talking about the coefficients of the Taylor polynomial, those are these guys. Those are the coefficients of the Taylor polynomial. Notice that my counter starts at 0. 0 factorial is equal to 1, as is 1 factorial. Now, if you replace c with 0, we have something called a Maclaurin series. So go up there and take all of those. Gosh, I didn't write with c is equal to 0. I want c to be 0. So all those terms would be gone. X to the first, x squared, and this would be x to the n. So all of the c's are gone, so I don't really need the parentheses. They look kind of goofy in there. But each of the c's above is replaced by 0. So Maclaurin series are kind of handy when you want to build a function near that represents a function near the origin. And then if this function is defined for all x, we can easily shift it left or right with our x minus c. All right, so I'm going to show you an example of how we can build a Taylor series for the cosine of x. So let's take, 3, 4, 5 derivatives of the cosine of x. All right, so we need f of x is the cosine of x. F prime is minus the sine of x. F double prime gives us minus the cosine of x. F triple prime takes us back to the positive sine of x. And then the fourth derivative gives us the cosine of x. And then we just recycle through the same values over and over and over. We want the center at c is pi over 3, so I have to evaluate each of these at pi over 3. Cosine of pi over 3 is a half. The sine of pi over 3 is square root of 3 over 2, so I've got a negative sign here, so negative square root of 3 over 2. Then we're here at negative cosine. Negative cosine would give us minus 1/2. And then we've got the third derivative at pi thirds is the sine of pi thirds. That's the square root of 3 over 2. And now we're going to cycle through these values again. We're back at a half. So it follows that pattern. So here's what we're doing. We're writing f of x as f of c plus f prime at c times x minus c plus f double prime at c times x minus c squared triple prime at c times x minus c cubed. Now remember, we've got to include the factorials. Let's see, I've got all the way down to the fourth derivative, so let's go ahead and put the fourth derivative in here. And then we'll just put dot, dot, dot. So in our example, we're writing the Taylor polynomial for the cosine of x. F and c is pi thirds, so I get 1/2 right here. Now I've got the negative square root of 3 over 2, so let's put minus square root of 3 over 2 divided by 1 factorial. Well, 1 factorial is just 1, but I'll put it in here just for the fun of it. Then you have x minus pi over 3. The second derivative at c was a negative 1/2. Times x minus pi over 3 squared over 2 factorial. Now the third derivative gave us the square root of 3 over 2 over 3 factorial times x minus pi thirds cubed. Then our fourth is back to a half over 4 factorial times x minus pi thirds to the fourth plus, and so on. So the four numbers are going to repeat, but the polynomial is going to grow and grow and grow. So however many terms we want to put in here, we can put them in until we're tired of writing them. And I'm tired of writing them. But it's easy as that. You take derivatives, you evaluate it at the center, and then you fill in the formula. So let's do it again. Let's do it for the natural log of 1 centered at c is equal to 1. So let's take a few derivatives of the natural log of x. We have to keep the log of x here first. The first derivative is 1 over x. The second derivative is negative 1 over x squared. The third derivative is going to be 2 over x cubed. The fourth derivative looks like a negative 6 over x to the fourth. I've got room for a few more. The fifth derivative, let's see, that would be 24 over x to the fifth, and so on. Then we need this centered at c is equal to 1. The natural log of 1 is 0. F prime at 1 is 1. F double prime at 1 is negative 1. F triple prime at 1 is 2. The fourth derivative at 1 is negative 6. And the fifth derivative at 1 is 24. Okay, so our polynomial, following our formula up there, that f of x is f of c plus f prime at c over 1 factorial times x minus c, f double prime at c over 2 factorial, x minus c squared dot dot dot. So we're going to have, let me kind of buckle this off here. We'll have that the natural log of x is equal to the natural log of 1, which is 0, plus the first derivative is going to be a 1 over 1 factorial times x minus 1. The second derivative gives me a negative 1, so let's go ahead and put the negative 1 here. Times x minus 1 squared. The third derivative is 2 over 3 factorial times x minus 1 cubed. Oops, don't need that twice, silly. Okay, and so the fourth derivative would be a negative 6. Then here I'd have a 4 factorial and an x minus 1 to the 4th. Then we're going to have 24 over 5 factorial times x minus 1 to the 5th, and so on. Now, remember that, let's see, did I leave myself some room for the next one? Oh, I did. Here we go. But let's see, let's make some observation here. Let's look at the 24. 24 is the same as 4 times 3 times 2 times 1, or 4 factorial. And that 6 up there is 3 times 2 times 1, so that's 3 factorial. The 2 is 2 times 1, so that's 2 factorial. So these numbers right here can be written as factorials. Even this one, that one would be 0 factorial. So we can write the natural log of x, let's ignore that 0 right there. We can write the natural log of x as 0 factorial divided by 1 factorial, which simplifies to just 1. Minus 1 factorial over 2 factorial. That's just going to simplify to 1/2, right? 2 factorial. I guess I could have written that as 1 over 1. 2 divided by 3 factorial. Well, if I take 2 and divide it by 3 factorial, that's 2 divided by 3 times 2 times 1. That's just 1/3. So I get a plus 1/3 here. And then the 6 over 4 factorial. 6 is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So 3, 2, 1 will cancel, leave us with a 1/4. And they got a minus sign there, so minus 1/4 times x minus 1 to the 4th. Then the next one's going to simplify in the same way. I have 4 factorial divided by 5 factorial is just 5, or 1/5. And it's going to be an alternating series. The next term would be a 1/6 times x minus 1 to the 6th, plus 1/7 times x minus 1 to the 8th. Okay, so it looks like something that we can kind of predict. Has a nice pattern to it. Okay, let's look at the next example. We want to write a Maclaurin series for f of x is e to the x, and then I'll show you how we can use it to get a Maclaurin series for g of x is e to the x squared. So let's take a bunch of derivatives of e to the x, and they're all going to be e to the x. And at 0, e to the 0 is 1. And so we can write, here's the general formula again, f of x. It's Maclaurin series, so c is equal to 0. So we write it as f of 0 plus f prime at 0 times x over 1 factorial plus f double prime at 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed over 3 factorial, and so on. And so in this example, let me pull it down here, e to the x looks like e to the 0, which is 1. F prime of 0 is 1 over 1 factorial, so that's going to be x over 1 factorial. F double prime is 1 times x squared over 2 factorial. F triple prime is 1 times x cubed over 3 factorial, and so on. So I can go ahead and generalize that this looks like x to the n over n factorial, right? In fact, we noticed a couple of examples ago that if n goes from 0 to infinity, x to the n over n factorial is the way we can write this series in its summation form. Now, on its interval of convergence, we can do term-by-term substitution. So if I wanted to approximate the value of e squared, I just put a 2 in here, and I can get a rough approximation of e squared. If I wanted to know what e to the square root of x looks like, I replace each x with the square root of x, and so on. So in this one, I want to give a Maclaurin series for g of x. Let me do that in red. E to the x squared can be obtained by replacing each x with x squared. So I'm going to have an x squared over 1 factorial plus x squared squared over 2 factorial plus x squared cubed. Oop, I lost a factorial here. X squared cubed over 3 factorial. And the general term would look like x squared to the n over n factorial. Or in its summation notation, it would look like x squared to the n over n factorial. And I suppose we can go ahead and simplify this enough. X to the 2n over n factorial. Now think about how hard it is to say integrate e to the x squared. Can't do it. Not in closed form, but we know that on its interval of convergence, we can integrate a power series term by term. So we can just integrate term by term. Integrate this one and get an x. Integrate the x squared, and we're going to get x cubed over 3, and then we've got that 1 factorial. Integrate the x to the 4th, and we have x to the 5th over 5 times 2 factorial. Integrate x to the 6th, and we get x to the 7th over 7 times 3 factorial. And depending what our needs are, we would just integrate term by term. So when we integrate that, we add 1 to the power, divide by 2n plus 1 times n factorial. Isn't that cool? And then if we wanted to do a definite integral, now we would just evaluate each of those terms on the indefinite integral. Right? We can integrate term by term. We can differentiate term by term. And we've shown in a previous example that the interval of convergence for this particular power series was all real values of x. You can do that with the ratio test and show that no matter what x is, this has a limit smaller than 1. Now I'm going to show you how I can find a Maclaurin series for an expression without having to take an infinite number of derivatives. So there are some tricks of the trade. So here I want the Maclaurin series for 1 over 1 plus x squared, and then we're going to use this to find the Maclaurin series for the arctangent of x. So the first thing I want you to remember is that if you have a geometric series with r smaller than 1, then it has a sum of a over 1 minus r. So if I begin with 1 over 1 minus, say, u, then I know that has the form of a geometric series. A plus ar plus ar squared plus ar cubed, and so on. So I'm using a as 1 and r is u. So it looks like a plus a times r plus a times r squared plus a times r cubed plus, and so on. Right? And now I'm going to, so that's a over 1 minus r, so I want a plus sign here. So I'm going to replace each u with the opposite of u. To give me 1 plus u. So replace each u with the opposite of u, and I get 1 minus u. The opposite of u squared is still u squared, but the opposite of u cubed is minus u cubed. So every even power is going to have a positive sign. Every odd power is going to have a negative sign. Now I'm going to replace u with x squared. And so I have 1 over 1 plus x squared. Looks like 1 minus x squared plus x squared squared minus x squared cubed. Raise a power to a power, you multiply exponents, plus x squared to the 4th minus x squared to the 5th, and so on. And so look at that. I've got power series for 1 over 1 plus x squared. It's an alternating series. Let me see if I can write it in closed form. I'm going to need a negative 1 to the k, and I'm going to start my k out at 0 so that my first term is a positive 1. And then my powers all have to be even. So I'm going to put an even number up here. So if k is 0, I get x to the 0 times a positive 1. If k is 1, I get a negative 1 times x squared. When k is 2, I get the x to the 4th and a negative 1 squared. So there's my claim that the general term looks like that. And so if I wanted to know the interval of convergence, I can do the ratio test on this. But I know the interval of convergence. I began with the geometric series where the absolute value of r is less than 1. So in here, I know that the absolute value of u has to be smaller than 1. Then I replaced u with the opposite of u, but it's an absolute value, so that still holds. And then I replaced u with x squared, so this holds for x squared smaller than 1. Well, x squared is smaller than 1 whenever x is smaller than 1. So there's the interval of convergence. Now, use this to find a Maclaurin series for the arctangent. Okay, I recognize that the arctangent of x can be found by integrating 1 over 1 plus x squared. So I integrate term by term. Integrate 1, integrate the x squared, integrate the x to the 4th, and so on. Or I can go to the general term. I'm going to have a negative 1 to the k. Integrate that, and you get x to the 2k plus 1 divided by 2k plus 1. So notice that when k is 0, I get negative 1 to the 0, which is going to be a positive 1, x to the 1 over 1. When k is 1, I get a negative sign, x to the 3 over 3. And so there is the power series expansion for the arctangent of x. It has the same interval of convergence. It converges for the absolute value of x less than 1. All right, so in the next example, find a Maclaurin series for the sine of x. Use this to give the Maclaurin series for the cosine of x. So let's start taking a bunch of derivatives. Again, a Maclaurin series is centered at c is equal to 0. So let's start with the sine of x and take a bunch of derivatives of it. Derivative of sine is the cosine. Derivative of cosine is minus the sine. Derivative minus the sine is minus the cosine. And now at the fourth derivative, we're back where we started. So we're going to recycle through those numbers again and again. Now we need f of 0. Sine of 0 is 0. Cosine of 0 is 1. So here I get a negative 1. And so on. So what this is telling me is every even derivative of f is going to be 0. Every odd derivative of f is either 1 or negative 1. So when we build this polynomial, here's the Maclaurin formula, f of x is equal to f of 0 plus f prime at 0 times x over 1 factorial plus f double prime at 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed over 3 factorial, and so on. So we have f for sine of x, we have 0 plus 1 over 1 factorial times x plus 0 times the x squared plus the next one is a negative 1 times x cubed. The next one is 0. Now I'm back at a positive 1 times x to the, that'd be 4, so that'd be x to the 5th. This has a 3 factorial. This will have a 5 factorial, right? Then I'm going to have another 0, and then the next one's going to be negative x to the 7th over 7 factorial, and so on. So let's simplify that the sine of x looks like x, let's just write it over 1 factorial, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. So let's see if we can write it in closed form. Let's see. So the first one, I've got to have a negative 1 to the k. So the first one's a positive 1. So let's start at 0. And then we're going to have an x to the k plus 1 over k plus 1 factorial. So that every other power, the odd powers are, I gotta get odd numbers, so we better go with a 2k plus 1. Right? 2k is even, so 2k plus 1 is odd. We just want odd numbers in here. Right? If k is 0, down here I have 0, 1 factorial, x to the 1. If k is 1, I get a negative sign, powers of 3 over 3 factorial. K is 2, I get a positive sign, powers 5 over 5 factorial, and so on. Okay, and so that's the general form for the sine of x. Let's see, do I have room here, yeah, I think I can find the power series for the cosine of x. The cosine of x is found by taking the derivative of the sine of x. Also, I could have integrated, but then I would have to worry about the negative. So, to get the power series for the cosine of x, I take the derivative, term by term. So when I differentiate the x, I get 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. If I differentiate in this form, this is a constant. I bring the power down, raise it to 1 power less, and then I still have this 2k plus 1 factorial. Now again, we can cancel. 3 factorial is 3 times 2 times 1. So that 3 cancels here and just leaves me 2 times 1. 5 factorial is 5 times 4 factorial. So that cancels and leaves me a 4 factorial. That cancels and leaves me a 6 factorial. This cancels and leaves me a 2k factorial. And so in its pretty form, I can write that as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So another alternating series. Okay? Have you ever heard that the sine was an odd function? Look at all the powers on its power series. They're all odd numbers. And the cosine is an even function. All of the powers on its power series are even numbers. And if you wanted to find the interval of convergence, then you just do the ratio test. I'll save you some time on this. All of this stuff is in table form, and I want you to look at the table. It's in your text, and I'll try to remind you of this. We should know the power series, or the Maclaurin series. Let's get the Maclaurin series. Remember, those are the ones that are centered at c is equal to 0. Know some of the basic ones. If you know some of the basic ones, then you can, by substitution or derivatives or antiderivatives, find some of the other ones. So the important ones to know are e to the x, sine and cosine, and the inverse tangent, the geometric series. These are in your text on page 660, and so it's good for you to know the Maclaurin series for the sine of x, for the cosine of x, for e to the x, for the geometric series, for the inverse tangent. That one I wouldn't really worry about knowing, but if you know it, again, you can do these in general, e to the u instead of e to the x. So the geometric series that looks like 1 plus u squared plus u cubed plus u to the 4th, right? That should sum up to 1 over 1 minus u. The sine of u was the odd one, so that's u minus u cubed over 3 factorial plus u to the 5th over 5 factorial minus u to the 7th over 7 factorial. And so if you know that one, then you automatically know the cosine, or you can figure it out by taking derivatives. Right? So this one would look like 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus u to the 6th over 6 factorial. And so that one's got the even powers. Negative 1 to the k, u to the 2k over 2k factorial. This one was the 1 plus u squared over 2 factorial plus u cubed over 3 factorial. So that was u to a power over k factorial. And then you can just get this one by integrate term by term. We'd have to make that change in variable, but it would look like u minus u cubed over 3 plus u to the 5th over 5 minus u to the 7th over 7, right? Because I'd have to replace the u with a minus u and then a u with a u squared. So that's why all these powers are jumped up by 1 and so on. So know those, and then you can do some fancy stuff and play with them. So look over those and we'll do some examples in class.